Hello, and welcome to Building Multi-Agent Systems with Strands Agents. My name is Laura Selenus, and I'm a developer advocate at AWS. Now, this is a part 3 in a 4-part series for Strands Agents. If you have not watched part 2, I have included here the link and a QR code to get familiar with that course, so make sure that you complete that. It's also free here on Analytics Vidhya. And then finally, here is a link to the repo with all of the coding examples that we will see in this course. Now, in the next video, we'll get started.
Hello, everyone, and welcome to Lab 1 in this third course of our Strands Agents series. Again, my name is Laura Selenus, and I'll be helping you navigate this course. I'm excited to guide you through an exploration of multi-agent systems, the patterns you should know about, and how it all comes together with the Strands Agents SDK. Now, let's get started. So what exactly is a multi-agent system? At its core, it's a system composed of multiple autonomous agents that interact with each other to achieve a mutual goal that's often too complex or too large for any single agent to do alone. You can kind of think of this as a well-orchestrated team. Just as humans collaborate by bringing different skills and perspectives to a project, AI agents can also specialize in different domains and work together to achieve superior results. Let's first start this lab by taking a look at what you'll learn. We're going to be defining what a multi-agent system is, cover common terminology and core concepts. We'll also explore 5 common agent patterns and understand how collaboration, negotiation, and emergent behavior play a role in multi-agent systems. Now, let's go to some key principles that govern effective multi-agent systems. Here's the definition for what a multi-agent system is, but let's talk about orchestration, which is a controlling logic or structure to manage the flow of information and tasks between agents. This is like having a conductor in an orchestra, ensuring everyone knows when to play their part. Next, we have specialization. An agent has a specific role or expertise and a set of tools that it can use. Rather than having generalist agents, we can create specialists. Maybe one excels at data analysis, another at natural language, and another at decision making. Finally, here we have collaboration. This means agents can communicate and share information to work upon each other's work. Now, this isn't just parallel processing, it's true collaboration where agents build upon each other's contributions. Next, let's discuss at a high level what these architectural patterns are, and then we'll dive into the specific patterns. Now, multi-agent systems can be organized using several different architectural patterns, each suited to a different type of problem. There's hierarchical systems. In these systems, we use a central orchestrator agent that interprets the overall task, decomposes it into subtasks, and then delegates to those worker agents, each optimized for a particular domain. This can mirror a traditional organizational structure with clear chains of command. Next, we can take a look at broadcast systems. In broadcast systems, information is shared broadly across all agents simultaneously. This can ensure that everyone has the same context, but it can also lead to information overload. Now, in a graph-based architecture, we allow for complex communication patterns where agents form networks of relationships. These agents may operate independently or with other agents by sharing information, dividing responsibilities, and collectively reasoning toward a goal. Now, we're going to start taking a look at the 5 fundamental patterns that Strands supports, and we'll go in at a high level with 4 of these, and then I'll point you to a resource for the 5th one. So let's look at that. Now, in the next 3 labs following this introduction, we're actually going to be diving into each of these patterns in depth with distinct characteristics and use cases and code, but for now, we'll just be introducing the concepts. So in this video, we're going to be taking a look at the core concepts and understanding the theory behind these patterns, and then in my following labs, we'll actually dive into some code. So let's take a look at pattern 1, swarm. The swarm pattern represents a dynamic, collaborative team of agents that autonomously hand off tasks. A developer provides a pool of agents, and the agents themselves decide what the path will be. In this flowchart that we see here, we can see what this is referring to in a swarm pattern, right? So we have a coder agent, we have a researcher agent, and we have a reviewer agent, and an architect, and they're all kind of dynamically collaborating. Now, the key characteristics here are autonomous decision-making for the handoffs, There's some emergent execution paths that will come up as the agent figures out, who to talk to next. And there's some shared context across the agents. Next, we'll take a look at workflow. So the workflow pattern represents a predefined task graph, or DAG, executed as a single non-conversational tool. Here, a developer defines all the tasks and dependencies in the code. Now we can see here in this next diagram what this kind of data pipeline workflow could be. So we have a researcher agent that's going to be talking to an analysis agent, which will then talk to a report agent. And it's a much more structured kind of one-to-one flow. Now in this pattern, the key characteristics are a predictable execution, it's excellent for repeatable processes, and there's some efficient parallel processing that can happen. Now finally here, let's take a look at the last pattern in this example, which will be graph. So the graph pattern combines the structure with the flexibility. So it's a structured, developer-defined flowchart where an agent decides which path it will take. A developer will define all the nodes, or agents, and the edges, or transitions, in advance, but the actual path is determined dynamically by the agent. So in this next diagram that we have here, we can see the researcher agent has the ability to call an analysis and fact-checking agent, and then they can talk to a reporting agent, and so on. The key characteristics here are, again, a structured but flexible architecture. There's some conditional logic and branching that can take place, and there's some pretty good error handling defined through each path. Now, for our fourth pattern, we'll talk about agent as a tool. This is the last of the common patterns, and we are basically saying that this is an architectural pattern in an AI system where specialized AI agents are wrapped as callable functions or tools that can be used by other agents. Now, here's an example here in this diagram. So my user, or myself, I'm interacting with an orchestrator agent, and this agent is doing a lot of delegating and talking to a research assistant, talking to a product recommendation assistant agent, and a trip planning assistant agent, but I'm calling them as tools. So that's a bit of a different concept. Okay, so some key characteristics for this agent as a tool pattern. There's clear separation of concerns. This is, again, a hierarchical delegation, and there's a modular architecture that's easy to maintain. So I can plug and play different agents as I need because I'm kind of using them as tools, as I call them in the code. Now, finally here, I wanted to discuss a new pattern, which is not traditional to the four previous patterns, but this is the agent-to-agent protocol, or A2A. Now, the fifth pattern here represents a breakthrough in multi-agent architecture where we separate it, again, from the traditional four patterns mentioned before. And with agent-to-agent, which was announced in April of 2025, it's an open standard that enables AI agents from different platforms, organizations, and implementations to discover, communicate, and collaborate seamlessly. The protocol is now backed by a growing ecosystem of partners, including over 50 technology companies like Google, Atlassian, Salesforce, etc. Now, in the diagram here, which is from the official A2A documentation, we're basically seeing kind of a network diagram showing agents from different platforms communicating via the protocol. So there's an agent on the left-hand side here, and it has some sub-agents, and then it's talking via the A2A protocol to other agents that may be living in other ecosystems. So that's kind of a different approach to agents. Now, unlike the previous patterns, which operate within a single system, A2A creates a distributed ecosystem where agents can work across those organizational and technical boundaries, like I mentioned. Each A2A enabled agent exposes what's called an agent card, which is basically a standardized description of its capabilities, skills, and interfaces. We have actually covered A2A already in a lab in our first course of this Strands Agent series. So I'm actually going to take you over to take a look at what that is so that you're familiar. If you haven't completed that course, you can go back and take a look at that. Okay, so like I mentioned, if you haven't completed course 1 of this Strand series, again, this is part 3, I recommend going back and checking out lab 5 in course 1, which walks through a coding example featuring A2A with strands. And I'm just showing that here. So if you actually were to navigate over to course 1 of this same series, this is the kind of main page for it. But when you actually go in and navigate to it, the 5th lab here is that agent-to-agent communication, where my coworker Ellie goes into a Jupyter notebook describing how Strands plays into A2A and how you can use it. There's also, alongside with the course, there's also this GitHub repository, which has that A2A communication Jupyter notebook that I mentioned, which is what Ellie is covering in her lab. So just make sure to go back to that if you want to get hands-on with A2A. This course 3 will cover swarm, agents, graph, and agent as a tool in depth, but it won't be covering A2A. So make sure to go back and cover that. Now, some of the key characteristics for A2A, again, there's multi-agent workflows, so you can chain multiple specialized agents together across platforms. There's also an agent marketplace where you can discover and use agents from different providers. Of course, one of the big benefits of A2A is this cross-platform integration, so you are able to connect agents built with different frameworks. And there's a distributed AI system underneath it all, so you can build kind of a scalable distributed architecture by leveraging A2A. Now, in this final section here, we'll talk about collaboration, negotiation, and emergent behavior. So what makes multi-agent systems truly powerful is how these agents can collaborate and sometimes negotiate on the best way to achieve an optimal outcome. So what are collaboration mechanisms? We basically are saying that each pattern handles collaboration differently. In a graph system, a single shared dictionary object is passed to all agents who can freely read and modify it. In swarm systems, there's a shared context concept, so a working memory is available to all agents containing the original request, a task history, and knowledge from previous agents. Now, with negotiation and decision making, we can look at the swarm pattern especially, where agents must negotiate who should handle what tasks. This isn't pre-programmed. The agents are using their understanding of the problem and their capabilities to make these decisions autonomously. Now we can move on to the final concept here, which is perhaps most fascinating, emergent behavior, which is basically a complex problem-solving pattern that arises from simple agent interactions. We can take a look at a swarm here, where a swarm might develop unexpected but highly effective solution paths that no single designer anticipated. And this is an interesting diagram here that kind of illustrates that, where, for instance, in a customer service swarm, agents might develop a novel escalation pattern based on customer sentiment analysis, creating a much more effective resolution path than what had been previously predefined. So this diagram kind of illustrates that, where we're saying, in traditional AI, there's an input, there's a program logic, and then there's a predictable output. But with emergent AI, as these agents are kind of traversing through different ways of solutioning, we find even better ways to actually get to a solution. Okay, so that's all for today. We've explored the 5 fundamental patterns for multi-agent systems. So that's agent as a tool for hierarchical delegation, swarm in emergent collaboration, workflow for structured automation, graph for controlled flexibility, and A2A protocol for cross-platform distributed collaboration. Now, when we take a look at some of these key principles, we're basically talking about choosing the right pattern, which is critical for building an effective system. What you can consider, whether you need something more deterministic or perhaps are expecting some more emergent behavior, the type of complexity of the problem that you're looking to solve, and the requirements, if any, for parallel execution or error handling. These are all things that you want to keep in mind as you're building. Now, as AI systems become more sophisticated, multi-agent architectures will enable us to tackle increasingly complex challenges by harnessing this collective intelligence of specialized AI agents working in harmony. Now, in our next lab, we'll be diving deeper into the swarm pattern for multi-agent systems. So don't forget to come back and check that out, and check out all of the course resources for additional documentation. Thanks again for joining me, and I'll see you in the next lab. Welcome back. My name is Laura, and in this lab, we'll be learning more about the swarm multi-agent pattern and look at coding implementations with the Strands Agents SDK. Now, in our previous video, we learned at a high level what a multi-agent system is, and I introduced the 5 common agent patterns. Let's take a look at what we'll cover in today's lab. First, we'll define the swarm pattern. This is a bit of an overview of what we covered in the first lab, but we'll go into a little bit more detail here. We'll also review how Swarm, the pattern, operates in the Strands Agents SDK. And we'll go ahead and implement a basic agent swarm with a Jupyter notebook from our sample GitHub repository. And then finally, we'll review some best practices and take a look at when it makes sense to actually use this pattern versus some others we'll cover later on. Now, before we dive in, it's important we understand why Swarm as a pattern even became a topic in AI. So let's understand swarm intelligence and nature. We can think of an ant colony where thousands of individual ants are each following simple rules, but together they're building a complex structure. They're finding optimal food resources, they're adapting to challenges, and in reality, no single ant directs the colony, yet collective intelligence emerges. And we can see how this applies to our swarm pattern here. Now, we've defined this earlier, but agent swarms apply the same principle to artificial intelligence. Instead of one powerful agent trying to solve everything, we can create multiple specialized agents that work together as a team, the same as the ants do in nature. Each agent has its own expertise, but they share knowledge and coordinate their efforts. And again, this diagram that you see here, we shared in the first lab, but it's just a reminder of how swarm intelligence works. So in this case, we have a coder agent, a researcher, a reviewer, and an architect, and they're all talking to each other, have shared knowledge, and can hand off tasks appropriately. So again, to review some of the key characteristics of agent swarms, they're able to self-organize teams with shared working memory. There's tool-based coordination between the agents. There's autonomous collaboration without a central control. So there's no orchestrator in this case. There's dynamic task distribution based on each agent's capabilities, and they can share that with each other, what they're each specialized in. And then there's collective intelligence through shared context, and we'll take a look at what that looks like in a second here. Now, the magic that happens through emergent intelligence is this idea that a group of specialized agents working together can solve problems more effectively than the most sophisticated single agent. Let's explore how agent swarms actually operate. In the Strands Agents framework, each agent in a swarm has access to these four critical components. First, there's full task context, so every agent sees the complete problem. Next, there's an agent history, so the agents know which other agents have worked on the task. There's shared knowledge, so the agents have access to insights from other agents, and they know what the other agents have done to date. And there's a built-in handoff capability, so they can transfer control of the task to other specialist agent. So what does that actually look like? This is when we can talk about coordination mechanisms built into the Strands Agents SDK for the swarm pattern. So effective coordination is basically what separates a swarm from just multiple agents working separately. The Strands framework provides these built-in coordination tools. The first one that I want to introduce here is the handoff tool. So the handoff tool allows agents to transfer control precisely. And we can inspect this example here on my screen where the handoff tool will give an agent named Coder the context it needs and let it implement the necessary Python code. And that's this example here from the Strands documentation. Next, there's an additional built-in capability that is shared context. So shared context ensures that every agent has a full picture. When an agent receives a handoff, this is what they see, and we can take a look at the example here. There's a handoff message explaining why they were called. There's the original user request. So this is basically what we are telling the agent in our prompt. There's which agents have also worked on this task previously. And there's the additional shared knowledge from all previous agents. And then finally, there's a list of all the other available specialists that these agents can call upon. Swarms in Strands also supports multimodal inputs, so not just text, but images as well. This means that your swarm can analyze diagrams, process reports, and then generate a comprehensive analysis, all-in-one workflow. I don't demonstrate that here, but I'll have you take a look at the Strands documentation to look at that. And this is done via something called context blocks. Okay, let's move on to some practical implementation in code. First, we'll describe what we'll be doing in the code, and then we'll jump right into the Jupyter Notebook. So to get a high-level understanding, creating a swarm involves 3 key steps. First, you define your agents. Next, you create the swarm and configure behavior and safety parameters. And this is an example here of the configuration parameters table from the Strands documentation. These are some of the parameters that you can control. There are things like max iterations, so the maximum total iterations across all agents, you can set that. You can also set the total max number of handoffs in your swarm. And then there's some other interesting parameters that you can control, like preventing ping pong behavior, and that would be the repetitive handoff detection window. And then finally, going back to the 3 steps, you'll want to just execute and analyze the results of your swarm. The swarm constructor can return detailed results, including things like execution status, complete or fail, which agents have participated, individual agent outputs, performance metrics, and token usage statistics. And we'll take a look at that in the Jupyter Notebook as well. All right, we'll jump into the coding part of this lab now. You can find the Jupyter Notebook that I will be referencing here in the course repository, and I'll throw in a link here as well if you're watching this video so that you can access that. But I've basically cloned that repository locally in my IDE, and I'll be interacting with that Jupyter Notebook from there. So let's dive in. So I have here that Jupyter Notebook that I've referenced, and there's a lot of useful information here. A lot of it we've already covered in the rest of this video. So I'm just going to be diving into the cells and kind of walking you through what is happening here. So as we start with this notebook, there's 2 sections of the notebook here. The first one, as we'll see, is actually using Swarm as a tool. So built into the Strands Agents SDK, there are 2 options to use the swarm pattern. You can either use it via a tool, so that is using the Strands tools package, and then you can import the dependency for swarm, or you can actually just use the swarm capabilities in the Strands SDK directly. So this notebook will take a look at both methods. The first one here that we'll open up with is actually using it as a tool. So to set ourselves up here for success, I have a Python virtual environment that I am running locally here to run the rest of this notebook. So I'm going to be executing each cell, and we'll just be explaining things as they happen. So first cell here is just going to be installing a lot of the requirements for this Jupyter Notebook to run properly. You'll see that I have a lot of that already installed. Next here, because we're going to be using the Strands Agents SDK, we have to import the agent class from the Strands library, and we'll also be importing Strands tools, we'll be importing Swarm from the Strands tools library as well. And then next here, this is a really straightforward use case. When we're using Swarm as a tool, it's as simple as this. So 2 to 3 lines of code, and you can get up and running with Swarm as a tool. A couple of things that I want to point out here. This Jupyter Notebook is using Bedrock, Amazon Bedrock, as the model provider, and that's why you'll see the call out to an endpoint for US Anthropic.Claude 3.7. This is using the default model provider for Strands agents, which is Bedrock. We've shown in course 1 and course 2 of this series how to use other providers directly. So that means having your own API key. In course 1, I covered how to use Anthropic and OpenAI, as well as Light LLM directly in your use cases for Strands. This notebook, though, uses Amazon Bedrock, so you will have to have your AWS credentials set up in your CLI for this notebook to run. So if you're getting any errors locally when you run this notebook and you're getting permissions errors, it's likely because you have not set up your AWS credentials, and I will include some links in the course resources for how to do that, but we do cover that in course 1 and course 2 to make sure that you're set up with AWS CLI credentials. So let's say you've got all that set up, so this will work properly for us. But in this case, the agent class that I'm defining here will be using the Anthropic Claude 3.7 model. And then I'm passing in that swarm tool that I've imported earlier up here. And then next, I'm just going to be invoking the agent with natural language and going to be giving it some pretty simple instructions here for what to do. So use a swarm of 4 agents to analyze the current market trend for generative AI-based agents. So I'll run this cell and we'll see what it comes up with. Now, this is going to be a streamed response. So the Jupyter Notebook here will probably truncate at some point, but we can see what starts to happen here. At the very first part of this result, we'll see the agent kind of iterate through what it needs to do. So it restates the user problem, it takes a look at the tools that it has, so the swarm tool, and then it goes ahead and actually kicks off the process. And we see that it's building a report. I'll probably fast forward through this part as it does this on the back end. All right, so it looks like this cell has completed executing. It took about 1:49. And we'll save ourselves the trouble of reading through this result and actually just go ahead and print the result directly to the console so that it's a little bit more legible. I'll go ahead and open it up here as a scrollable component. So this is what that agent swarm has created. So let's just go back and remind ourselves what our prompt was. So we asked the Strands Agents SDK to use a swarm pattern and to create a swarm of 4 agents to analyze the current market trend for generative AI-based agents. So we're expecting a report here of the current market trends. So let's take a look at what happened here. So we have a report here, market trend analysis, generative AI-based agents. We can see that there's some information about market size and growth, key players, some specialized agent platforms, investment trends, etc. Now, this is a pretty comprehensive report. It shows us some challenges, ethical considerations. It even does a future outlook into 2029. So this is pretty cool. That swarm has completed and it gives us a kind of recap of everything that it's done here. So it created the market analysis. Now, I don't know about you, but in this notebook, it doesn't actually show us what the agents have been doing behind the scenes with the swarm. So I'm actually going to just ask the agent directly, what agents did it use to complete the previous task? And we'll see what it's telling us here. Because when we take a look at the output, the market trend analysis that it generated is not necessarily something that a single agent couldn't do on its own. So I'm curious why, what kinds of patterns it found and why it felt like it needed to create certain specialized agents over others. So let's see what the agent did. So it's telling us, I used a swarm of 4 specialized agents to analyze market trends. Here's the specific agents. So again, these are agents that the swarm decided it needed to create and then created and leveraged. So we see one here for a market analyst. This agent was focused on analyzing market size. There's a different agent that was an industry expert, another one that was an application specialist, and then another one that was a strategic forecaster. And that's probably how we got that future outlook for 2024 to 2029. And then it even tells us, based on the execution results, the collaboration chain shows that the work started with the market analyst and then was passed to the strategic forecaster who completes the task. So, okay, that's pretty interesting. Now, we didn't have much control here, as you saw, with what agents it created, what were the system prompts. We really just gave it one question and then let it run. And that's what we're doing when we use Swarm as a tool. So this may be helpful in some areas where you may want to let the models be a little bit more creative and you perhaps don't need to be as deterministic in what specifically your chain of agents should be doing. But I want us to take a look at the next example in this notebook where we get a little bit more prescriptive and can actually control aspects of the swarm. So in this next section here, we're diving into how to use the Strands Agents SDK to actually create the swarm piece by piece. And this references that 3-step process that I called out earlier when we were reviewing some of the concepts. So I talked about defining the agent, configuring behavior and configuration parameters, and then executing and analyzing it. So that's what we'll do in this next section here. This Jupyter notebook has an example of a swarm that we will create that has these 4 agents, and we'll see the handoffs happen and we'll inspect it step by step. So in this example, we'll also be taking a look at the handoff to agent coordination tool that we talked about earlier as well, and we'll see how that plays into this particular example. So in this next cell here, we are actually going in and defining each specialized agent. So differently to the first example where we just let the tool basically do its own thing and create the agents as it needed. In this case, we'll be really specifically defining what each agent should do. So in this case, let's just review what we're doing before we execute the cell. So there's 4 agents here. The first agent is a research agent, and it has this given prompt. You're a research agent specialized in gathering and analyzing information. We give it its role in the swarm and some parameters about, what it should be focused on. And then we give that a name, as we can see here. And we also define the model. So you can have different agents use different models if you recognize that they may be better suited for a particular model versus another. And this will also be an important factor when you're using multimodal support, if you're using images and text in your swarms. In this case, these are all text-based agents, so we're not really using anything different than Claude 3.7 Sonnet. So we'll see how that all plays into effect. But let's go ahead and execute this cell just to get those definitions set up. So we see that that has completed. Next here, because we're doing this manually, we have the ability to control those parameters that I talked about earlier. So we're going to be importing from strands.multi-agent the swarm class here. And with the swarm class, we have the ability to, again, manually configure those behaviors and parameters that are specific to the swarm. So first here, we'll see that we pass in the 4 agents that we've defined above. And then when we define that swarm, we're going to be controlling specific elements of its behavior. So we want a maximum handoff of 20. We want a maximum iteration also of 20. We want the execution timeout to be 15 minutes for this entire swarm. So this will prevent, and 15 minutes is a little bit generous here, and you can manipulate this as you want. But in this case, the execution timeout is basically telling the swarm, if you're going to be taking longer than 15 minutes, stop and time out, because we don't want you to be running into potentially infinite loops. So that's what we control here with the execution timeout. And then in the node timeout, this is specific to each agent. So again, we have 4 agents, and we want them, in our case, to not take longer than 5 minutes per agent to complete a task. Again, this is preventing hopefully some infinite loops, and you can move around this time as you see fit if 5 minutes is too long or too short, depending on the complexity of the task that you have given it instructions for. You can iterate through time here. Let's go ahead and execute this cell here. And then finally here, this is the actual task that we will be giving this swarm of our 4 agents. So what we want to be doing is creating a blog post explaining Agentic AI, and then also creating a draft for a social media post to promote that said blog. So there should be 2 deliverables here that we are expecting from the swarm. So let's go ahead and take a look at what it does. And actually, one thing here that I'm actually going to add in, there's another parameter that you can control within the swarm, which is this entry point parameter, which is basically telling our swarm to start with the research agent and then figure out how to do some handoffs. You can include that, you don't have to include that, but I've played around with this notebook a little bit and I found that it actually works a bit better if I tell it where to start. So the original notebook that you will have when you download this repository might not have this line here, but you can add it if you want, if you're noticing some behavior where it's not actually using the research agent. So I'll go ahead and execute this cell here. So that's complete. Now we're going to be giving the swarm the task that we wanted to complete. So let's go ahead and execute that cell. And again, this is going to be doing a streamed response. So it's going to take a little bit here, and I'll probably fast forward through till it's done, and then we'll take a look and inspect all of the results. So we'll do all of that once this cell completes. Okay, so it looks like that cell finished executing. It took about 47 seconds. And let's take a look at what our swarm has created for us. So at the very top here, we can see the first tool is a handoff to an agent. So it's processed the user request, and it says here, creating a blog post and media content is more aligned with creative work. So I'll hand off to the creative agent for better results. And then it tells us that it's handed off the creative agent for content creation. So the first part here, the swarm has started creating that blog on Agentic AI, and that ends right around here. And then finally here, we see that it has also created a social media post draft for probably something like LinkedIn. And so it's giving us a nice little blurb here about what the blog is about. So again, this is something interesting here that you can kind of inspect, is these are two different agents acting in a swarm, but my creative agent, or actually I think in this case it's probably the summarizer agent, we'll take a look, but the summarizer agent has created this social media draft based on the blog that a different agent in the swarm wrote. So there's some shared context here and some shared knowledge about what the previous blog was that I'm now able to use, or the swarm agent is now able to use to create a draft. So again, we're not seeing with too many specifics what exactly has been done, so we can inspect some other cells here to actually look at that. This next cell here just tells us, or just prints out whether or not that execution has completed. So that's all that does. Next here are some cells with some more interesting meat here. So you should expect in this example that it starts off with the research agent, which will gather information about Agentic AI, should hand off to the creative agent to then actually write that blog. Maybe might go through the critical agent to, double check for accuracy and completeness. And then finally, the second deliverable that we asked for was a draft promoting that blog for social media. And that's what the summarizer agent should do for us. So we can inspect what specifically has been done both at each node, so at each agent level, what has been done. And we can also take a look at some performance metrics here. So total iteration time, total execution time, total number of iterations as a count, total execution time in milliseconds, and then the total token usage. So let's go ahead and run this cell and see what we get here. So the first thing that we're printing here is a history of each agent that was involved. So in this case, it looks like there was the research agent involved and a creative agent involved. And it doesn't actually look like it ever got to that summarizer or critical agent. So that's interesting. And then next thing we're printing out here is what are the results of the research agent. The research agent has said to us, it's handed off the request to the creative agent who specializes in content. So that's interesting. There may be some use here for better prompting in our model to really specifically call out that it should use those agents that we defined in the swarm for which aspect of the task. So it looks like this run may not have actually done that exactly, but it still generated some content. Finally, here we see the total number of iterations. So there was 2 iterations, and then the total execution time, which was, again, like I mentioned, about 47 seconds. And then finally here, we are printing out total input tokens, total output tokens, and then the combination of the two. And we can probably play around with the prompting here in our swarm task to really specifically say which agents it should be using, though it should be able to do that on its own. So definitely encourage you to take a look at that as well, play around with it. But that's basically the example here. The swarm system automatically manages that agent coordination. So in this case, the research agent decides to hand off to the creative agent to write the blog. And all of that handoff mechanism is handled by Strands via the handoff tool that I mentioned earlier. The agents here autonomously decide when to transfer control to other agent specialists, and we're basically creating a seamless collaborative workflow here. Now, again, this is not a perfect system, and you can clearly see that here. So there may be some work to be done on our end here to improve the prompting and maybe even improve the descriptions of each agent, because it doesn't look like maybe we gave it enough clarity for Sonnet in this case to fully pick up when we want it to be handing off to a particular agent versus another. We'll take it back to the presentation for a quick recap on when to use Swarm, some best practices, and then what we'll be covering in the next lab. Welcome back from that demo. I wanted to finally cover some concepts here about when to use Swarm. So some things to think about: when your problem can be broken down into subtasks that benefit from different specialized perspectives, that's a great opportunity to use a Swarm pattern. Again, Swarm is ideal for things like exploration, brainstorming, or synthesizing information from multiple sources through collaborative handoffs, because it is leveraging that agent specialization and shared context to generate diverse, comprehensive results. These are some good places to use it. And some examples, if you're still a little bit confused about, what exactly we mean, when would be a good time to use Swarm versus not. Something like an incident response use case. So if we have a monitoring agent that can detect an issue that then hands off to, let's say, a network specialist that can diagnose the problem and then maybe hands it back to a database admin. That's the kind of idea that we're talking about here. Like we looked at in the Jupyter Notebook and in some of the documentation that you'll find with Strands, there's also use cases for software development. So perhaps a researcher that hands off to an architect agent who hands off to a coder who can hand off to a reviewer, and then the path becomes emergent as it's solving through that particular user request. Next here, let's take a look at some best practices to wrap things up. So when we're talking about best practices for effective swarms, these are some things to keep in mind. Make sure that you're creating specialized agents that are defining clear roles for each agent in your swarm. You can use descriptive names that reflect each agent's role, and also be sure to include descriptions of your agents to help other agents understand what their capabilities are. Make sure to set appropriate timeouts based on task complexity and runtime. If you know that a task may take 5 to 10 minutes, make sure to build that in so that your swarm is completing the task in the appropriate time. Alongside this, you can enable repetitive handoff detection, which we talked about earlier, to prevent that ping pong behavior of agents just handing each other tasks indefinitely. Make sure to include diverse complementary skill sets in your team of agents, and then enable safety detection to prevent some problematic behavior across agents. Finally here, I mentioned that the swarm pattern is able to support multimodal inputs, so make sure to leverage those using context blocks for rich inputs that include images when necessary. Let's take a look at some key takeaways and set you up for the next lab. Again, swarms enable that emergent intelligence through collaboration. Specialized agents can work together more effectively than a generalist. The shared context and coordination tools built into the Strands Agents SDK ensure coherent output, and there's safety mechanisms that prevent runaway processes, so we want to make sure you use those. Finally, multimodal support handles diverse input types. In our next lab, we'll dive deeper into the next multi-agent pattern graph. And don't forget to check out the course resources for additional documentation, the links to the sample GitHub repository that we covered, and additional resources. Thanks again for joining, and I'll see you in the next lab. Welcome back. My name is Laura, and in this lab, we'll be learning more about the graph multi-agent pattern and look at coding implementations with the Strands Agents SDK. Now, in our previous video, we dove into the swarm multi-agent pattern and walked through 2 coding implementations in a Jupyter Notebook with the SDK. Now, let's take a look at what we'll cover in this lab. We're going to define graph-based multi-agent systems, review agent graph components in the Strands SDK, implement an agent graph, and review best practices. Now, let's get started. Let's start with the fundamentals. A graph in Strands is a deterministic directed acyclic graph, or DAG for short. Think of it as a workflow where each agent has a specific role and clear dependencies. Unlike sequential workflows where agents simply pass results in a line, or swarms where agents collaborate dynamically, graphs provide structured coordination. Each agent knows exactly when to execute based on the completion of its dependencies. Let's review the graph pattern's key characteristics. First, it has deterministic execution order based on its graph structure. There's output propagation along edges and between nodes. There's clear dependency management between agents, and there's support for conditional logic and branching workflows. I like to think of it like a manufacturing assembly line, but for information processing. Each station or agent performs its specialized task only when its required inputs are ready. Now, let's talk about the graph components in the Strands Agents SDK. Every graph consists of 3 core components. We're going to walk through each one here. First, we have graph nodes. Each node here represents an agent or multi-agent system with a unique identifier, an executor, this is the actual agent instance, dependencies on other nodes, execution status tracking, and performance metrics. Next, graph edges define the connections between nodes. They specify source and target nodes and optional conditions that determine if the edges should be traversed. Finally, we have the graph builder. This provides a simple interface for constructing graphs. It lets you add nodes to the graph, create edges between them, set entry points for execution, configure timeouts and max executions, and also validates the graph structure. The beauty of this architecture is its simplicity. You define your agents, specify their relationships, and let the graph handle the execution and orchestration. Next, let's talk a little bit more about input propagation and context management. One crucial aspect of graphs is how information flows between agents. The graph automatically builds input for each node based on its dependencies. This means that an entry point node receives the original task as its input, and any dependent nodes receive a combined input that includes the original task description and results from all completed dependency nodes. Here we can inspect what the formatted input for a dependent node looks like. So we can see the original task, the inputs from previous nodes, etc. This ensures each agent has full context while maintaining clean separation of concerns. Now, before we get into the code, I want to review 3 common graph topologies, some of which we'll encounter in the Jupyter Notebook example. First, let's take a look at sequential pipeline. This is typically good for quality control workflows, and you can see in the diagram here what this would look like and what it takes to build it in code. Next, there's parallel processing. So Coordinator distributes work to multiple specialists and then aggregates those results. This is great for comprehensive analysis from different perspectives. And then finally, we have branching logic. A classifier determines which specialized branch to take, useful for routing different types of requests to appropriate specialists. All right, let's get into some code. So I have here the Jupyter Notebook that is in the same repository as Lab 2 that we covered in the previous video where we talked about strands with swarm patterns. So this is in that same repository, and I'll just show that here quickly. So in the same repository, this is the swarm agent lab that we did in the previous video, and now we'll be accessing the graph agent notebook down here. So that is all in the same repository. Now, this notebook has a lot of really useful information about graph and the pattern and things to be aware of within the Strands Agents SDK while you're building graph topologies. We've covered a lot of that already in the presentation, so I will be skipping through most of the text in here, and we'll just be diving into each cell and describing what we're doing in the code. So let's jump right in. Similar to the last lab, the first couple of cells are just some admin tasks. We'll be installing the requirements and then importing the agent class from the Strands package. So we'll go ahead and do that here. Next here, we'll be importing that agent class from the Strands package. All right, so that's completed. And now this section here will walk us through our first example. There are 3 examples for using graphs in this notebook. We'll walk through each of them. This first one here is the most basic scenario, and we will have this architecture, so a team lead, an analyst, and an expert agent. And in this simple task, we're basically just having the team lead delegate to the analyst and expert for a particular task. We'll go through how in the Strands SDK you actually define this architecture for a graph pattern, and then we'll go ahead and execute the task and see what our results are. So that's our architecture up there. Now in the code, this is basically how you would define that particular architecture. So the first thing we'll do here is we're going to import the graph builder class from strands.multi-agent. This lets us interact with the SDK that will actually be used for building graphs. So this will always have to be included if you are looking to build graphs with the SDK. Next here, we're going to be actually defining each of the agents that we looked at in the design earlier. So these are just arbitrary names, but coordinator, data analyst, domain expert, we'll see where these specific names up here are actually utilized, but these are just defining the agents themselves. And then we're giving each agent a system prompt. You'll notice that these system prompts are pretty basic. So just a caveat here, when you're actually developing, and we've talked about this with best practices, but when you're developing outside of a POC scope, you'll want to really tighten down these system prompts and make sure that they're as descriptive as possible so that the agents have really good understanding of what they're meant to be doing, not doing, etc. These are just simple one sentence prompts, but I wanted to call that out. Next, we will be actually creating the graph. So we call graph builder and pass that to, or save that to a variable called builder. And then now we are ready to actually build the relationships from the nodes and the edges. So what does that look like here? You do a builder.addNode and then just pass in the name of the agent that we created up here. So we're creating that coordinator, the analyst, and then the domain expert. And now you can see the names reflect the names of the previous diagram up here. So that's why those names are different than the names of the agents. These are the names of the nodes, and you can continue to define nodes here if needed. We'll see that in other examples. Next, we'll add the edges or the dependencies. And so edges in the graphs are basically the directions in which tasks will flow and how an agent knows that another agent is available downstream or upstream of it. And so in this case, we're adding two edges. The first is a team lead and analyst edge. So that would be this left arrow here. And we expect that the next edge would be a team lead to expert edge. So that's this arrow here. And that is how you build the graph. And then finally, once we've defined the nodes and dependencies, the last step is just to build the graph. So we'll do a builder.build and store that in a graph variable so that we can call that later on. Next here, this notebook does a little bit of formatting for us. So this is not required. It's just for readability's sake. So when we are printing the results for this task, this notebook has some new lines and some divisions here just to make it a little bit more legible, but this is not required. So when we say result equals graph, we're passing in the user task here, which is analyze the impact of remote work on employee productivity, provide a short analysis, no need for follow-ups. And we'll store that in the variable result, which we'll be accessing throughout the rest of this notebook later on. The next thing we'll do here is print out the node execution order. So because we are able to actually look and inspect at each of the node results, we're able to first take a look at what their execution order was. So we'll print out which of the nodes were utilized to execute that particular task. Then we will also look at some metrics of the graph. So all of these graph metrics are built into the SDK, similar to what we did with the swarm pattern in the last notebook. You can take a look at total nodes, completed nodes, failed nodes, execution time in milliseconds, and also print out the token count, so input, output, and then the accumulated usage. So that's what we're doing down here, is we're taking a look at some of those metrics. And then something else that you can do as well, if you wanted to inspect specifically the result of a particular node to perhaps troubleshoot or take a look at what a particular agent result was from a graph. So in this system, there's only 3 agents, so it's not that complex to figure out what each agent has done. But if we were building a multi-agent system where there's maybe dozens of agents, this might be interesting to be able to have the ability to inspect a particular node and what that node is bringing to the rest of the combined results. So we'll be taking a look at the results from the expert node and then printing those out to the console. So I will go ahead and run this cell and probably fast forward through this. All right, so it looks like that cell finished executing, took about 22 seconds, And I'm going to open up this scrollable element here so that we can actually look through all of the results. So starting from the top, we actually get a nice printout from the SDK here for graphs, giving us a note to make sure that we are not running a acyclic graph. So basically a graph that runs indefinitely in a circle. Looks like we're okay here though, because we've got a pretty thorough result. So starting from the top here, we had asked for, let's scroll back up. So let's look at the task again. The task was to analyze the impact of remote work and provide a short analysis. So we're expecting a short analysis on remote work from our 3 agents in this graph. So we'll see here that there's an analysis on key findings, a bottom line. So pretty short, kind of recap there of what was done, some data, some core impact assessments, etc. This is pretty standard for a report of this nature. But what's interesting here that I want to actually take a look at is what else we've been able to pull out from the graph. So the graph has completed, so we can see that here. And we can take a look at the node execution order. So if you remember, we wanted to print out what was being done as the graph traversed through its dependencies and how it actually got to the result that we just saw above with the report. So in our case, the 3 nodes were utilized. So the team lead, the expert, and the analyst were all utilized for this execution. And we can see some stats about the total nodes and completed nodes for this graph, the time it took, about 22 seconds, and then some metrics on input tokens, output tokens, and then the combination of the 2. And then, like I mentioned earlier, you can inspect the results from a particular node in a graph. So in this case, the sample notebook takes a look at the results from the expert node. And so that's what is being pulled out here. So that's that example. All right, so in this next example here, we'll be taking a look at parallel processing, which is a different topology that we mentioned in the presentation earlier. Again, there are 3 of these topologies that we covered: sequential, parallel, and then branching. We'll take a look at parallel and branching in the next 2 samples here. So in this demonstration, we'll be looking at this setup for a graph. So there's a finance expert, a tech expert, a market expert, and then a risk analyst. Now this is also referred to as a mesh. So you might see that in some other documentation, but parallel and mesh are sometimes used interchangeably. Now in this case, there's a problem that we would like the agent to solve, and we want inputs from both a tech expert and a market expert that will then be assessed by a risk analyst to generate the final summarization and a risk calculation based on those inputs. And the code here demonstrates what it's like to build this type of mesh design topology. So in this case, very similar to before, we're still importing the graph builder to build this graph. We are setting up the agent class with the name mesh agent, and then we'll be creating those specialized agents. So again, we'll be using the financial advisor, tech advisor, market researcher, and risk analyst. Same setup here. This is a simple, 1 or 2 sentence system prompt, and we're storing that in these variables here. Next, we'll actually start creating the graph. So in this case, we do the same process as before. We add the 4 nodes, which are the 4 agents that we'll be utilizing. Now, the difference here is how we're actually setting up the dependencies. So when we add those edges, as we can see in the design above, the finance expert is never really talking to the risk analyst, and the risk analyst is not, dependent on the finance expert per se. It's dependent on the tech expert and market expert. So we would expect that the edges here that we're building are based on that design. So we have an edge for finance and tech expert, and we have an edge for finance and market expert, which defines these 2 lines here in the diagram. And then we'll expect that the tech expert and risk analyst and market expert and risk analyst should have an edge of their own. So that is being defined here in these last 2 lines. So that's looking pretty good. And then finally here, we'll just go ahead and build it and store that in the graph variable. The task now for this group of agents is the following. Our company is considering launching a new AI-powered customer service platform. The initial investment is $2 million with a projected 3-year ROI, return on investment, of 150%. What's your financial assessment? And then in this case, we'll actually be printing out the results from 3 of the nodes in our graph. So we're printing out the specific results from the financial advisor, from the technical expert, and then from the market researcher. And we'll inspect all of those here. So I'll go ahead and execute this cell. And again, I'll fast forward a little bit to when that's done. Okay, so it looks like that cell executed here. So let's take a look at what our team of agents using the graph pattern came up with. I'll skip over a lot of the actual minutia of the report and just get to what we're interested in, which is how we came to these results with the graph pattern and what exactly the graph was doing to get to the solution. So when we print out the node execution order, we see that all 4 nodes were used. So the finance expert, tech expert, market expert, and then the risk analyst. So again, some info here about which of the nodes were utilized, how long it took, the input and output tokens. And then we're printing out, if you remember here, we wanted to print out the results from 3 of the specific nodes, finance, tech, and market nodes. So that's what this last section is giving us here. So it looks like from the financial advisor, we received this information, which was input on ROI, the key finance questions, and revenue model validation. The tech expert took a look at feasibility, the critical challenges for implementation, some technical risk factors, and then we should expect that the market researcher took a look at the bigger picture. So market researcher looked at size and growth of the market for AI, some market leaders, competitive analysis, etc. And then that all came together. So it looks like the results from those 3 agents came together to build us the comprehensive report that we saw up here. So our prediction here with the diagram succeeded, right? So we're seeing a bit more complexity within our graph example here, where we're actually giving a task to multiple agents to give their specific input as experts and then come together to give us a final result. Now, this is just a sample here for a demonstration of a tech expert and a market expert, but if you were to extrapolate this and really think about creating agents that are experts in a particular domain, perhaps with proprietary company information, or agents that are using a particular model that it has a strength in the task that they are completing. Just a reminder, we didn't talk too much about it here, but in our previous course, we talked about how you can give agents individual models to actually use as they're executing these tasks. So in our case, the sample notebook here uses an Amazon Bedrock model, but you want to use the best model for the task that your agent is performing. So in our case, we're performing traditional text-based tasks, so the model isn't being changed. But if I were wanting to create a report that also generated images or generated a physical PowerPoint or something like that, I would want to make sure that my agents are using the model that is appropriate for that task that I'm using. So just a good thing to keep in mind here. And now with that, let's move on to our final example here, which is the last topology that we covered in the presentation, which is the branching topology. Now in this use case, you can take a look at the diagram here, but we're basically doing something similar as the previous example, but now we're actually giving the model the choice to decide which edge it should traverse depending on how it interprets the user task. So if it's a technical task, it should interpret through the classifier and send the request to the tech report writer agent. And if the task is deemed to be a business task, then it should go through the business report writer. So we'll take a look at what that looks like here. We expect that the definition of the graph will change because now there's conditional logic. So we'll take a look at what that is. All right, so let's take a look at the code for this branching topology. So again, we're doing the same thing as before, importing the graph class, initializing the agent, and then going ahead and creating and giving a system prompt to our 3 agents, in this case, a classifier, a tech expert, and a business expert. We're building that graph, we're adding the 3 nodes. Now here is the difference that happens when we're using branching or conditional logic in a graph, is rather than building edges directly to these last 2 nodes or agents here, there is a piece of the code here, which I'm highlighting, that creates that conditional logic. So we're creating a state here where if the classifier result is technical, then it will go through this method here. If the state is business, then it will return business and be used as a business use case. So this is the definition for that logic that we're implementing up here, where the classifier will make a decision as to whether something is technical or whether something is business. and then actually use that result of technical or business as a label in the building of the edges and dependencies here. So because we have that definition of the logic here, we can now start building those two edges with the condition of is technical or is business, which is basically the classifier saying to us, this is a technical use case, this is a business use case, go through the agent path for that particular edge. And so that's what we're doing here, and that's how you can use this parameter of condition in this use case when you're using a branching topology. So let's go ahead and execute this graph and inspect the results. All right, so it looks like that cell finished executing here, and let's take a look at the results. So scroll back up here and we can start taking a look from the top. So there's some key technical considerations that were printed out here. This is a technical aspect of working from home. Now, one thing that I forgot to mention in the code here is there's actually two scenarios that are being processed simultaneously here. Now, you could comment out the second half of this code if you wanted to do this one by one, but in this case, we're printing both at the same time. So we're actually asking the agent both questions at once. So the first result here is to provide a report on a technical aspect of working from home. And then the second request here is to provide a report on the business impacts of working from home. And that's how we'll be basically doing both traversals in the graph for a technical and a business result. And we're printing both at the same time, so we'll inspect the results down here. Now at the very bottom here, we can first see that the technical aspect report is up here. Then we can see the final recommendation. Business report is then coming in at the bottom here, and we can see the key business impacts, risk factors, its recommendation, and then the resulting metrics. So this is pretty interesting because we're seeing the agent be able to handle two different use cases based on just the intent of the question. So it is interpreting that when I ask for technical aspect, it's going through the conditional logic and understanding that this should be sent over to the technical expert. And when I'm saying provide a business impact, it's understanding that it should use a business agent for this use case. Again, this is a simple demonstration, but you can extrapolate this to be something a bit more complex. And again, we'll talk a little bit later now that we come back to the presentation about when are the right use cases for the graph pattern. All right, welcome back from that coding example. Now, to start wrapping up here, let's discuss when to use the graph pattern. When you need a structured process that requires conditional logic, branching, or loops with deterministic execution flow, that's a great time to use this particular pattern. Another way to look at it is a graph performs well for modeling things like a business process or any task where the next step is decided by the outcome of the current one. Now, here's some practical examples. An interactive customer support call. So routing a conversation based on user intent, something like, I have a question about my order and I need human assistance, or things like data validation with some error paths built in. So perhaps an agent can validate data, and based on the outcome, a conditional edge routes it to either a processing node or an error handling node. Now let's review some best practices for using graph patterns. Design for acyclicity, so no circular dependencies. Use meaningful node IDs that reflect the agent roles. Leverage conditional edges for dynamic workflows. Consider parallelism for independent tasks. And make sure to handle failures gracefully with error conditions built in. Now, we've covered a lot of ground today, but you should now understand the fundamentals for multi-agent systems using the Strands graph pattern. In our next lab, we'll dive deeper into the final multi-agent pattern of this course, Agent as a Tool. Don't forget to check out the course resources for additional documentation, and thank you again for joining. I'll see you in the next lab. Welcome back. My name is Laura, and in this final lab, we'll be learning about the multi-agent pattern, Agent as Tools. Now, in our previous video, we dove into the graph multi-agent pattern and walked through 3 coding implementations in the Strands SDK with a Jupyter notebook. Now let's take a look at what we'll cover in today's lab. First, we'll define the Agents as Tools architectural pattern. We'll understand the tool decorator, which wraps agents as callable functions. We'll test the multi-agent system in a Jupyter notebook, and we'll finally review best practices. All right, let's dive in. So the Agents as Tools pattern creates a hierarchical structure with 2 types of agents. First, we have an orchestrator agent. This is like a manager. It handles user interaction and determines which specialized agent to call. Second, we have the specialized tool agents. We can have multiple of these. These are like domain experts. Each performs a specific task when called by the orchestrator. So why would we use this pattern? Let's take a look at 4 key benefits. First, there's a separation of concerns, so each agent has one focused responsibility, making the system easier to understand and maintain. There's hierarchical delegation, so the orchestrator decides which specialist to invoke, creating a clear chain of command. There's modular architecture, so you can add, remove, or modify specialists independently without breaking the entire system. And finally, improved performance, so each agent can have tailored prompts and tools optimized for a specific task. Now let's take a look at some of the components within the Strands SDK that make this possible. So we'll break down how this happens with the built-in @tool decorator in the Strands Agents SDK. This is what transforms our function into a tool that other agents can use. When using the decorator, the doc string is crucial because the LLM you set up to process the request reads this to understand when to use the tool. It's important to be descriptive and clear. You can also define a focused system prompt for the agent created and include error handling to gracefully manage any issues. You can take a look at the example here where we define a research assistant tool, give it a sense of what it should be capable of doing, and then implement some error handling logic in there. Next, let's discuss the other piece of this pattern, the orchestrator. The orchestrator is the brain of our multi-agent system. Its job is to understand user requests and route them to the right specialist agent. Here's an example of how it's built. Now, when we take a look at this, I want you to notice something important. We're passing the specialized agents, those functions that we created with the @decorator tool, directly into the orchestrator's tool list. The Strands SDK handles all the complexity of making this work. So we can see that here we're passing a research, a product recommendation assistant, and a trip planning assistant into the tools that this agent is aware of. Now the system prompt is also critical here as well. It gives the orchestrator clear guidance on when to use each specialist, similar to training instructions for a manager. And we can take a look at that here as well and inspect the main system prompt for this sample. Now let's move on to some code where we'll take this for a spin in a Jupyter notebook. All right, so now we'll be in the coding phase of this lab. So I have opened here the Agent as Tools Jupyter notebook. Now again, you can find this in the same samples GitHub repository that we've been working this whole course out of. This particular notebook that we'll be using for this lab will be in the tutorials, and then section 2 for multi-agent systems, and then agents as tools in the agent as tool folder here. So just make sure that you're in the right notebook, and it should look something like this. Now, again, I've described this in the previous labs, but these notebooks have a lot of useful information that we have already covered in the presentation part of this course. So I'll be skipping through most of it and just executing the cells and explaining what's happening as we do that. So let's go ahead and get started. Again, I'm running a Python environment in my Jupyter notebooks, so I will be executing these cells, and some of this will already be complete from previous labs. Now, first things first here, we're going to be importing the agent class from Strands package, and we'll be importing one of the pre-built tools called file write. And you can take a look at what that does, but in this case, it's just helping us write to our local system. And that's, again, a pre-built tool from the Strands tools library. So we'll go ahead and do that. And then you can also see here that we are importing from the Strands package this function called tool, which will be our tool decorator, and how we will be wrapping our functions to use as tools. Okay, so we'll go ahead and execute that cell. And now this is the diagram for the first sample that we'll be working through. So there will be a user who is giving a question to an orchestrator agent who will then decide which specialized agent should be handling that task based on how we've defined those agents and the doc strings, etc. So we have a research agent or assistant, we have a product recommendation assistant, and we will have a trip planning assistant. And based on what we're asking, the LLM underneath this will be able to decide which path to take. So we'll move along here. The first step we'll do is to actually create that research agent. So again, we're creating this first assistant here. There's a couple of different ways to do this. This notebook first does a system prompt. So here is the system prompt, your specialized research agent, focus only on providing factual information, etc. We'll go ahead and execute that to create that system prompt. Next here, we've done this, again, similar to other labs, but we'll basically be defining an instance of that agent class, calling it research agent, which is, again, that agent that we'll be using for the rest of this demo. In this case, this model is specifically being called out as an Amazon Bedrock endpoint for Claude Sonnet 3.7. So that's the model that will be used here. Now, again, I prefaced this in lab 2 and 3, but if you are running this notebook locally and leaving all the cells as is, you will need to have the AWS CLI configured and set up with your AWS account for these cells to execute properly. Otherwise, if you have an API key for another model provider that's not Amazon Bedrock, you can go ahead and insert that here, and just the code will change a little bit, but it should be pretty straightforward. As an example, I did this in a previous lab and just used an Anthropic API key directly. So this is basically the main change that you will do if you are not using Amazon Bedrock. Again, this is an example with Anthropic, and you can reference course 1, lab 2, where I spoke about using different model providers with Strands. So if you're confused on how to do that, check out that video or check out the documentation. We'll be using the 3.7 endpoint here, so all good there. We're passing in the system prompt via the variable that we saved earlier. Now we'll be doing a quick query here to make sure that everything is working well by just saying, what's an overview of Amazon Bedrock and its features? So we'll go ahead and print that. And here we have that in real time. So this is a streaming response. So we'll get that as the model is thinking through this. Here's a scrollable element, which makes it a little bit easier to read. So here's our overview. Okay, so that looks good. So we know that the agent is working, but we've not used it as a tool yet. So now, because of the concept that we learned earlier with the add tool decorator, we can wrap this agent that we've just created as a tool and have other agents interact with it. So that's what we're doing here in this next cell. So we'll use the add tool decorator, and then we'll define that research assistant. Here's that doc string that I mentioned in the presentation. That's really important. So as Sonnet 3.7 comes in here to this tool and tries to reason through what this tool does, this doc string will provide it that information about how to use the tool, what's expected as a return, what are the arguments that we need for it, etc. Then we have this pretty simple but helpful error logic built into the tool, so that if something goes wrong while the agent tries to use the tool, it has an escape path and can give us an error. So we'll go ahead and execute this cell. Now, again, all we're doing here is wrapping the previously created agent, which was a research assistant, into a tool so that we can call it with other agents. So we'll go ahead and execute that here. All good there. And now we can just finish creating the other 3 agents that will be involved in this multi-agent pattern. So if we go back up here to just remind ourselves, we have the research assistant now wrapped up as a tool. We have to create the product recommendation assistant, the trip planning assistant, wrap those up as tools, and then also create the orchestrator agent, which is who will be deciding which appropriate tools to use based on our request. So that is what is happening in the rest of these cells. Same process as before, except that now we're defining the product recommendation assistant. We have its doc string, we have its error logic, so we'll go ahead and initialize that. And here we can just test out that that agent is working. So we can say, give us a product recommendation for flying cars. This is obviously mostly silly, but just to double check that our agent is working properly before we move on. Great, so we've got that response. Next, we'll be building and wrapping up the trip planning assistant as a tool. Same thing as before, doc string, system prompt, the model, and then some error logic. And then finally here we have that orchestrator agent. We mentioned in the presentation that the orchestrator is what's going to be handling a lot of this heavy lifting for us. So on the user end, the user will just be inputting a query, and then the orchestrator will handle figuring out which specialized agent should be utilized based on the information that it has with its doc string and the system prompts, etc. But we have to give our orchestrator agent an understanding of what we expect it to do. So that's what we're doing here in the main system prompt. So we're saying you're an assistant that routes queries to specialized agents, and then a description of what those agents are, right? So we have for research questions, use the research assistant tool. For product recommendations, use that tool. For travel, etc., etc. And for simple questions not requiring specialized knowledge, you can answer directly. Now we could also say if any of the requests fall outside of these options, just say that you don't know the answer. So that's a common pattern when we have agents that we want to prevent from hallucinating. We can try to really explicitly in the prompt say, just do not answer that question if you don't have information on it. Great, so we'll go ahead and initialize that cell. And then finally here, we are just creating that agent. So we have the system prompt for it. And in this next cell, we're just creating that instance of the orchestrator agent, again, using 3.7 Sonnet as the model. And here is where we pass in all of the tools available to the orchestrator. So there are also other tools that we could pass in here, but in this case, we created 3 that we mentioned earlier, and we're also passing in that pre-created tool for file write, and we'll see where that comes into play. So let's initialize that cell. And now here's our first example of putting the whole thing together. This is a mock e-commerce customer service system. My customer query is, I'm looking for hiking boots, write the final response to that question into the current directory. So that's why we have this built-in file write tool, which will help us, or help the agent rather, write to my local directory. And in this case, there is a parameter for asking for consent from the user. Now, typically, we definitely want to keep this as false so that we are in control of what the agent is doing. But in this case, I know that I just am asking the agent to write its response to, I'm looking for hiking boots, to my local system. So I will bypass that consent with this statement here. But just a caveat, you definitely don't want to do this in production. This is just because I have a closed loop system here. I know what's happening. So I'm going to be able to do that so that I don't have to go in and give it permission as we run this. And then finally here, we want the response to be the answer that the orchestrator provides given that customer query. So let's go ahead and run that and see what happens. So we can see that the model is saying, great, I'll help you find those hiking boots. It looks like I have to first use the product recommendation assistant based on the information that I have about what I should be doing. Here are some suggestions. And then finally here it says, I know that you've told me I should write this response to the current directory, so I'll go ahead and do that. And it uses that second tool, file write. And so we see that here, the operation, it has just done a hiking boot recommendations text file. We have some information about what it wrote character-wise, and there's that text file. Perfect. So that has worked. Now let's take a look at what happened underneath the hood so we can see what the agent was thinking about as it successfully gave us an answer for hiking boots. So when we run this message, orchestrator.message, we can inspect basically everything that was happening, the communication behind the scenes between the agent and the model back and forth. So we can see here, this is the user request. I'm looking for the hiking boots. This is what the agent is responding with. So I'll help you find those hiking boots. It understands that because it's looking for hiking boots, what are some good recommendations for different quality boots? It's asking that of the product recommendation assistant. Here's where we see the tool use. So the response to that. Perfect. Now I have to write this file to the current directory. Looks like it's calling that file write tool and just goes ahead and writes that file, and the agent just tells us, great, we've successfully written it to the local directory. Okay, now let's take a look at a different query where we say, can you help me plan my trip to Patagonia? Now again, this is the same multi-agent system with a different question. So we would expect that it now routes this request to a different agent. Let's take a look. Okay, same thing. I'd be happy to help you plan that trip. And immediately we're seeing it's going right to tool number 3, trip planning assistant, because of the context it has. I'm asking a question specifically about travel, so I should be routing this request to the proper assistant, which is the travel planning assistant in this case. And same concept here. I'll make this a little bit more legible for us. But here is that model's response to my trip question about Patagonia. Great, so that's there. And we can do the same thing. We can inspect what was going on behind the scenes. So when we open up that message, we can see both actually the history of the previous message. So here's the history of what we asked earlier with the hiking boot recommendation. So there's some context here from the previous use. And then here is the current question that was just answered. So there's a question about helping plan my trip to Patagonia. And then here is the text that came from that use of the assistant with travel planning. Okay, now for our next example here, we'll be calling multiple agents based on a user query. So we'll go ahead and set this up for ourselves. The next cell here is that question. So can you do research on Spain? And then also help me plan a 7-day trip. So let's see how the orchestrator handles this response. Again, we have 3 assistants that it has available for its use: the research assistant, the trip planning assistant, and a product recommendation assistant. So it looks like it'll help us with both requests. First, it's going to gather some information about Spain. It's pulling that 4th tool and it's using the research assistant. So here it's getting together some information about the country of Spain. We'll see that it's generating and printing these results in a streaming fashion. So I might fast forward here just to get us to the end. Okay, so it looks like that cell finished executing, took about 1 minute and 4 seconds. And when I scroll back up, I want to just take a look at what it's done. So again, we mentioned that the first thing it did was use that research assistant that we gave it access to, and it gives us some general information about the country of Spain. Now, finally, here we have that next question that's being answered, which was to give us a 7-day itinerary for Spain. So now it's using the trip planning assistant. It understands that it did research before with the research assistant, and now we're going to be creating a 7-day itinerary. So here's that itinerary: day 1, day 2, etc., all the way down to day 7. And here's just a recap of kind of what it included, which is perfect, right? We were expecting that it would first call that research assistant, it would then call the trip planning assistant, and then combine both of those responses into a cohesive answer that we could interpret easily. And so that's the example there for using multiple of those tools at once with one query. Now, finally, here we have some sequential agent communications, which basically means that the agent tool can also combine multiple of these agents together. In this example, we will provide output of the research agent to a summary agent and then return those responses. So the main difference here that you'll see is we have to define a topic for a research agent to take a look at. And so in this case, same as before, Claude Sonnet 3.7 will be the underlying model that we'll use. We're passing in that same research assistant prompt and then creating a summary agent with this prompt. Now, in this case, we want to be taking a look at when each of the agents has finished successfully. So that's why we're printing this here. And we can take a look at what the research agent is working on based on the topic. So in this case, we're invoking the first research agent to say, please gather comprehensive information about the topic, which is generative AI. And then once that's done, once that research agent is done, we'll then be passing off that response to the summary agent. So we're asking that summary agent to create a concise summary of what's been done with the research text. So that's why we're saving that response from the research agent into this variable called research text. And then we'll be passing that research text variable with the stored response to the summary response agent to then give us a summary of. So let's go ahead and execute this cell. So we can see the first thing here, research agent is working on generative AI topic. Here is the information from the research agent. That looks like it's done already. So perfect. Here is the research agent's response. And then we can see that summary that was created with the summary agent. So pretty quick and concise here. This is definitely brief. Okay, perfect. So that is the end of this notebook here. Now, these are just been a couple of examples for how to use agents as tools when you're calling them from the Strands Agents SDK. We've done a lot of this too in the previous lab. So with course 2, when we talked about MCP and using agents as tools, this is more of a deeper dive into how that actually worked, what the tool decorator was, etc. Now we'll go back to the presentation to just finish up some last points. All right, welcome back from the coding examples. Let's recap what we've learned today. You saw that the @tool decorator is your gateway to wrapping agents as tools. It transforms any Python function into something another agent can call. And remember, the orchestrator handles that user interaction and intelligently routing the requests on your behalf. Now, here's some best practices to keep in mind as you use this pattern. First, write clear, descriptive docstrings. Again, the LLM uses these to understand when to invoke your tool. Keep your system prompts tightly focused on each agent's domain. Include error handling in every tool function. And finally, give your orchestrator explicit guidance on when to use each specialist. Now, you've learned how to implement the Agents as Tools pattern using the Strands Agents SDK, and this completes all the labs for Course 3 of this Strands Agents series. Now, don't forget to check out the course resources for additional documentation, links to the GitHub repo where we used all of the notebooks, and more. Thank you again for joining me, and stay tuned for our final course on this series where we talk about Agent Core. Happy building!